Imagine standing beside one of Europe's busiest shipping channels, watching some of the world's largest cargo ships sail toward the port of Rotterdam. Everything appears normal. The river is open. Trade never stops. Millions of tons of cargo continue moving across the globe. Then, weather satellites detect something terrifying. A powerful North Sea storm, combined with an exceptionally high tide, is heading straight toward the Dutch coast. Within hours, millions of lives could be at risk. Entire neighborhoods, critical highways, power stations, and one of the world's most important ports faced the threat of catastrophic flooding. Most countries would rely on emergency evacuations. The Netherlands does something different. It closes the river, not with sandbags, not with temporary flood walls, but with two floating steel giants, each longer than 2 football fields. Machines so enormous, they can seal an entire waterway in just a few hours, hidden in plain sight. The Maeslant Storm Surge Barrier is one of the most extraordinary moving structures ever built. A machine designed for a single purpose, to stop the sea itself. But how do you build a barrier that remains invisible almost every day, yet can suddenly become the last line of defense for millions of people? To answer that, we have to step inside one of the greatest engineering projects of the modern world. The Netherlands has always lived with water. Nearly 1/3 of the country lies below sea level. For centuries, the Dutch built dikes, canals, windmills, and pumping stations to keep their land dry. After the devastating North Sea flood of 1953, the country launched the Delta Works, a massive network of dams, storm surge barriers, locks, and flood defenses. Most of those barriers permanently close vulnerable waterways. But Rotterdam presented an impossible challenge. Its harbor is one of the busiest on Earth. Closing the river would protect the city, but destroy one of Europe's most important economic lifelines. Leaving it open would leave millions exposed to catastrophic flooding. Engineers needed a solution capable of doing both, keeping the river open every day, while closing it only when nature became too dangerous. The answer would become a masterpiece of mechanical engineering. Rotterdam isn't just another port. It is the largest seaport in Europe, and one of the busiest anywhere in the world. Every year, hundreds of millions of tons of cargo pass through its terminals. Container ships, oil tankers, LNG carriers, bulk cargo vessels, and massive offshore equipment all rely on unrestricted access to the North Sea. Building a permanent dam across the river was never an option. It would immediately cut off international shipping, cripple trade, and damage the Dutch economy. Yet the city remained vulnerable. Storm surges moving inland from the North Sea could force enormous volumes of water directly toward Rotterdam. Scientists calculated that a sufficiently powerful storm, combined with high river discharge, could flood vast sections of the metropolitan area. The economic damage alone would reach tens of billions of dollars. Protecting Rotterdam required something entirely new. Not a dam, not a traditional floodgate, but a movable barrier, large enough to close one of Europe's busiest waterways, while remaining completely out of the way during normal conditions. It was an engineering challenge unlike anything attempted before. When Dutch engineers first presented the concept, many believed it couldn't be built. The proposal sounded almost impossible. Construct 2 floating steel gates, each weighing thousands of tons. Store them beside the river, out of the shipping channel. When a dangerous storm approaches, rotate both gates across the waterway. Fill enormous ballast tanks with water. Allow the structures to sink onto the riverbed, forming a temporary wall strong enough to resist one of the world's most powerful storm surges. Then, after the danger passes, pump the water out. Float the gates back to the surface, and reopen one of Europe's busiest shipping routes. Everything had to work perfectly, every time, because failure wasn't an option. The safety of millions of people depended on it. Even more remarkable, the barrier would remain and used for years at a time, waiting silently, until the sea demanded its attention. Designing the Maeslant barrier was one challenge. Building it was another. Nothing on this scale had ever been attempted. Each of the barrier's 2 floating gates measures approximately 210 meters, making them longer than 2 football fields placed end to end. When standing upright, the steel truss structure rises nearly as high as a 20-story building. Together, the 2 gates weigh more than 6,000 tons. Yet despite their enormous size, they had to move with extraordinary precision. Unlike a traditional dam, these gates could not remain fixed. They needed to float, rotate, sink, and rise again without losing structural accuracy. Engineers first constructed the giant steel arms inside massive dry docks beside the Nova waterway. Every weld, every steel connection, and every hydraulic component was inspected repeatedly. The structures had to withstand decades of saltwater corrosion, violent storms, constant wind loads, and the immense pressure created by millions of cubic meters of moving water. Building something this large was difficult. Building something this large, that also had to move flawlessly, was an entirely different level of engineering. If there is one component that truly defines the Maeslant barrier, it isn't the gates, it's the hinges. Each steel arm is connected to land by an enormous ball and socket joint. These aren't ordinary mechanical bearings. Each steel ball measures roughly 10 meters in diameter, making it one of the largest ball joints ever built. Every joint weighs hundreds of tons. Its purpose is deceptively simple. Allow an entire flood barrier, weighing thousands of tons, to rotate smoothly and precisely during every closing operation. When the barrier begins moving, the massive steel arms slowly pivot around these giant spherical bearings. Despite carrying unbelievable loads, the movement appears almost effortless. That's because every surface inside the joint was machined with incredible precision. Tiny alignment errors could have created enormous stress throughout the structure. Engineers spent years testing different materials, lubrication systems, and load distributions before construction even began. Today, those massive joints quietly support one of the largest moving machines on Earth. Most visitors never notice them. Yet without these engineering masterpieces, the entire barrier simply couldn't function. Most flood barriers rely on gates that slide, lift, or swing into place. The Maeslant barrier works differently. When a dangerous storm surge is predicted, computer systems issue the command to close. The dry docks open. The 2 enormous floating gates slowly leave their resting positions. Powerful hydraulic systems rotate each steel arm toward the center of the river. The movement is surprisingly slow, not because the machinery lacks power, but because precision matters more than speed. As the gates approach one another, advanced positioning systems continuously monitor their location. GPS, laser measurements, hydraulic pressure sensors, and computer-controlled guidance systems ensure every movement remains perfectly synchronized. When both gates finally meet, the closing sequence enters its final stage. Large ballast tanks inside each structure begin filling with water. The floating gates gradually become heavier. Slowly, they sink onto a specially prepared concrete sill on the riverbed. Within a short time, the open shipping channel disappears. In its place stands a temporary wall strong enough to resist one of the most powerful storm surges the North Sea can produce. It is an extraordinary transformation. A river used by some of the world's largest ships becomes completely sealed by 2 floating machines. The Maeslant barrier isn't closed by politicians or by engineers watching the weather from a control room. The decision begins with data. Every second, thousands of sensors positioned across the Dutch coastline collect information from the North Sea, the rivers, and the atmosphere. They measure sea level, wind speed, air pressure, wave height, river discharge, and tidal movement. At the same time, weather satellites track developing storms hundreds of kilometers away. Supercomputers combine this information with advanced hydrodynamic models capable of predicting how storm surges will travel through the North Sea. If forecasts indicate that water levels in Rotterdam could exceed approximately 3 meters above normal Amsterdam level in AP,
Yes.
the Maeslant barrier automatically enters its closure sequence. Human operators remain inside the control center, carefully monitoring every step. But under normal conditions, the computer makes the critical decision. Why? Because during an extreme storm, minutes matter. Waiting too long could expose millions of people to catastrophic flooding. Closing too early could interrupt one of Europe's busiest shipping routes. The system constantly balances safety, accuracy, and economic impact. It represents decades of engineering, computer science, meteorology, and risk analysis working together as a single intelligent machine. Most engineering projects are designed to operate every day. The Maeslant Barrier is different. It may remain open for years, without ever being used. Yet when the moment arrives, it must perform perfectly. The first time, every time. That's why reliability became the foundation of its design. Every major hydraulic system has redundant backup units. Critical sensors are duplicated. Power can be supplied from multiple independent sources. Communication networks are protected against failures. Even the software controlling the barrier undergoes continuous testing and verification. Several times each year, engineers perform full operational exercises. The giant gates leave their dry docks, rotate across the river, fill with water, and sink onto the riverbed, exactly as they would during a real emergency. Afterward, the entire sequence is reversed. Compressed air forces water from the ballast tanks. The gates regain buoyancy. Hydraulic systems rotate them back toward their storage docks. Shipping traffic resumes to passing vessels. Everything appears routine, but behind every successful test lies thousands of hours of inspection, maintenance, and engineering analysis, because protecting millions of lives leaves no room for uncertainty. Even when the weather is calm, the Maeslant Barrier is never ignored. Teams of engineers monitor the structure every day. Specialized drones inspect the steel framework for corrosion. Underwater robots examine the concrete sill and submerged foundations. Laser scanners detect microscopic structural movement. Hydraulic cylinders are tested under controlled conditions. Lubrication systems are carefully maintained. Every bolt, every bearing, every electrical connection, and every mechanical component is inspected according to strict maintenance schedules. The giant ball joints, among the largest ever constructed, receive continuous monitoring to ensure they remain perfectly aligned. Engineers also simulate future storm scenarios using digital models. Some storms have never happened before, but the barrier is tested against them anyway, because the goal isn't simply to survive yesterday's disasters. It's to prepare for tomorrow's. For the people responsible for the Maeslant Barrier, maintenance isn't repair, it's prevention, and that philosophy has become one of the defining principles of Dutch flood engineering. For years, the Maeslant Storm Surge Barrier stood quietly beside the river. Ships passed through every day. Tourists admired its enormous steel arms. Engineers performed routine inspections. To many people, it looked like a monument, but it wasn't built to be admired. It was built for the day the sea came back, when severe North Sea storms threatened the Dutch coast. The barrier entered operation exactly as engineers had intended. Weather satellites detected rapidly deepening low-pressure systems. Wave buoys recorded rising seas. Computer models predicted dangerous storm surge levels moving toward Rotterdam. The automated warning system activated. Shipping traffic was halted. The giant dry docks slowly opened. For the first time, the enormous steel arms began rotating toward the center of the Nova waterway. Thousands of tons of steel moved with remarkable precision. No sudden motion, no dramatic explosions, just carefully controlled engineering. Once both gates met, ballast tanks filled with water, the floating structures slowly descended onto the concrete sill beneath the river. Within hours, one of Europe's busiest waterways had become a solid defensive wall. Behind the barrier, water levels remained under control. Millions of people, critical infrastructure, industrial facilities, and one of the world's most important ports remained protected. The system had done exactly what it had been designed to do, not by fighting the sea with force, but by understanding it, predicting it, and responding at precisely the right moment. The Maeslant Barrier was designed for the challenges of its time. But engineers are already looking far beyond today. Global sea levels continue to rise. Climate scientists project stronger storm surges, more extreme rainfall, and increasingly unpredictable weather patterns throughout the coming decades. For the Netherlands, standing still is not an option. Researchers continuously study how the barrier performs under future climate scenarios. Digital twins simulate storms far more powerful than those experienced today. Artificial intelligence analyzes millions of data points, helping engineers identify weaknesses long before they become problems. New materials with greater corrosion resistance are being evaluated. Hydraulic systems are being modernized. Control software receives regular updates to improve accuracy and reliability. At the same time, Dutch engineers are developing the next generation of adaptive flood defenses. Some concepts include intelligent storm barriers capable of responding even faster, while others explore nature-based solutions that combine engineering with restored wetlands and coastal ecosystems. The philosophy has never changed. Protect people, respect nature, prepare for the future before it arrives. Because flood protection is not a project with an ending. It is a commitment that must evolve with every generation. Every day, thousands of ships pass through Rotterdam. Without giving the Maeslant Barrier a second thought, millions of people go to work, children go to school, factories operate, and one of Europe's largest economies continues as normal. Few ever stop to consider the machine quietly waiting beside the river. A machine that may remain motionless for years, yet must perform flawlessly when called upon. The Maeslant Storm Surge Barrier is more than steel, more than hydraulics, and more than advanced computers. It represents centuries of hard-earned knowledge, lessons written by devastating floods, refined through science, and transformed into one of humanity's greatest engineering achievements. Its massive floating gates remind us that true engineering is not measured only by size. It is measured by trust. The trust that millions of people place in a system they rarely see in action. The trust that every sensor, every hydraulic cylinder, every computer, and every steel connection will perform exactly as designed. When nature is at its most powerful, the Netherlands never claimed it could defeat the sea. Instead, it built a machine capable of living beside it, one that predicts danger, responds with precision, and quietly returns to waiting once the storm has passed. Perhaps that is the greatest lesson the Maeslant Barrier offers the world. The future of engineering is not about overpowering nature. It is about understanding it, working with it, and creating systems so intelligent that they protect millions of lives without interrupting the ordinary rhythm of everyday life. Standing silently at the entrance to Rotterdam, the Maeslant Storm Surge Barrier remains one of the largest moving structures ever built. A masterpiece of mechanical engineering, a triumph of Dutch innovation, and proof that sometimes the strongest wall is the one that moves.